I just want to give a brief recap of where we're at here. Part one of this, I reviewed optical measurements. I made some initial points about the very large energy scales that we need to confront when we're trying to characterize materials. I made the point that particularly interesting to us, if we're interested in cooperative phenomena of solids, is the terahertz range. Right. One of the things we struggle with is having to deal with all the different ways of measuring units, and we're going to come back to that again today. But again, terahertz is quite important to us. 1 terahertz corresponds to tens of degrees Kelvin, so that typically tends to be an energy scale that we're quite interested in. I gave a bunch of examples of what we can do with linear terahertz response. Right? Optical conductivity is what we measure, let's say in metals. There are other optical responses that we can measure, looking at magnetic insulators. I didn't talk about those so much. Then in the part 2 was starting to talk about nonlinear optics, right? So the point that I made was that nonlinearities are a part of any dynamic driven system. The linear response is the simplest, and we really like linear response because even though it's simple, it's powerful. We can do a lot of things with it. That was indeed the first lecture. But nonlinearities generically exist. They can be an important source of phenomena, and they can be an important source of information. We need to be careful because the complexity can multiply faster than the information can multiply, and so we need to approach the situation cleverly. The technique that I was going to emphasize here, and I'm talking about, is this one here, terahertz 2D coherent spectroscopy. And again, just as a recap, recall that I said I wanted as a cartoon you to kind of think about 2 driven oscillators, weakly nonlinear. And I was going to plot the nonlinear response of the system in coming out of the board as such, right? And so a nonlinear oscillator has its frequency shifted when I drive it. And so if I pump it at the right frequency, when I probe it later, I can see that it was probed there. And similarly, let's say for the green oscillator and the red oscillator, and if that's a very different situation now, if I couple them together, where I form these off-diagonal peaks. And the point that I wanted to make is that you can say rather model-independent things about this. There are certainly, if I introduce some coupling, some projections, some effects in the linear response. These peaks will broaden, they'll shift, they become asymmetric. If I have a good enough theory, perhaps I can make some story about this coupling, but I seldom have good enough theory. But in the nonlinear response, it's not a matter of that. You see off-diagonal peaks where they didn't exist before. Right? The other thing we can do is perhaps look at some continua here where maybe I have many oscillators which are spectrally overlapping, perhaps all narrow, and in which case I would get this kind of streak along the diagonal. The linear response would just be this uninformative blob, but I can look at the cut in this direction here and get out the lifetime in this fashion. Okay, okay, good. So that's what data looks like. Okay, we're going to look at some of this again. Imagine, again, I'm performing this protocol. I imagine doing an experiment with just pulse A, just pulse B, A and B together, and then their difference, right? So this is the pulse separations and some kind of detection time. That's what the actual data looks like there. We're sweeping these 2 pulses apart from each other. And again, A and B together, and then the difference. And the difference is kind of by definition going to be all the nonlinearities. Yeah, Steve.
Just to make sure I have the strategy. This is like trying in MR to distinguish between homogeneous and inhomogeneous.
So that would be that, yeah. So there's commonalities here to what happened in other techniques. It's kind of, as the example I gave, is kind of like a hole burning experiment, right? So it's kind of similar to that. The advantage of 2D, it's one of the disadvantages as well, but it's also the advantage of it, is you basically get the full set of all nonlinearities, chi3 nonlinearities show up in this. And so that's one of the reasons. What's that? And hole burning is one of them. Yeah, exactly. Okay.
What is x-axis that time, EOS time?
Yeah, so it's kind of a technical term, electro-optic sampling time. But just imagine that it's like kind of like the lab time. So like if I was just to do 2 experiments, to do an experiment and send 2 pulses, I might see these 2 pulses come one after another here. Like, one comes here. Of course, if I'm measuring, I can't tell the difference between them. But, imagine I get, 1 pulse comes and another one comes in close, following it right afterwards. And then I might go and change the difference between these 2 guys. And that's this here, right? So here is where they're almost overlapping. And then I could overlap them, and that would be here. and I can sweep, let's say, the red guy through the blue guy, and that would be, moving along this line here as I sweep one through the other. Okay, good. Then I spoke last time about what we can learn, and this was the plot I showed you because I wanted to scare you. And if that's the classical electric field, and that's the nonlinear polarization, again, defined in this fashion is using one field to drive the system, using the other field to drive the system, and then using both together and forming the difference. That was this big mess here. And we see, one, that it's not so bad because everything comes in complex conjugate pairs. But two, if I start looking up in the exponent here, I see that there's kind of a frequency structure. And that frequency structure manifests itself in this two-dimensional spectrum, right? So that's the 2D of 2D spectroscopy. It's a two-dimensional spectrum, where now you might think of a normal old spectrum. We might call that a 1D spectrum, but this is a 2D spectrum, right? And those different contributions that I showed on the previous plot appear at different places in this plot, and they correspond to different processes, right? Okay, good. Okay, and I think that's where I stopped last time, if I'm not mistaken. So I don't know if there are any questions about this before I go on. Yeah.
So I've seen some theory papers where they try to calculate not just the location of the peak, but like the shape. And they get like some information about disorder from the like asymmetry of specific.
Yeah. So
Is that something that can
sure. Well, I mean, to make a cartoon, yeah. So I'll show some data like that. To go back to the cartoon I showed of these pendula, the streak along the diagonal, that's telling me something about the distribution of energy scales that are there, the distribution of the oscillators that I had. The width in the other direction has something to do with a lifetime. And in fact, what we'll see on the next slide, the next few slides, is how we can, there are different time scales, different relaxation rates, and we can be sensitive to those in different ways in a manner very similar to what happens in NMR. Okay, right, so there are these different oscillations, these different contributions, and we can refer to them in either way. Let me just point this out because we'll come back to it at the very end. That's the pump probe response. And so this corresponds to like a factor of E, a factor of E star, E times E star, that's intensity. So this is like putting, absorbing a photon in the system, if you will, leaving it in a little bit of an excited state, and then interrogating it at some later time. Okay, good. And then, yeah, as second harmonic response. Okay, good. So now, how do we understand this? So things can be complicated, so we want to be clever about what we do, and one of the ways that we're often clever in physics is we take complicated problems and we map them onto problems we already understand. And so that's what we're going to do in a number of these cases here. A problem that we understand is a two-level system, right? And so the way we're going to think about understanding the physics of the complicated problems that we've mapped onto a two-level system, as well as two-level systems themselves, in terms of what's referred to as a perturbative scheme for understanding the time evolution of the density matrices, right? So that's my density matrix for a two-level system. This guy here, 1, 0, 0, 0, that's the density matrix in the ground state. And what I'm going to imagine is I come in with a pulse that, for making my life a little bit simple, I'm going to assume is a delta function, okay? We can account for its width, but here we're just going to imagine it's an impulse and functions as a perturbation on the density matrix. And this is an extra term after this perturbation that I can add this little part here, which are these off-diagonal parts, which are come in the form of an antisymmetric matrix. Okay, good. So that's the scheme. And now when I come in and imagine that, if I had the full chi3 response, I have 1, 2, 3 pulses that I would interact with the system. And then, if you recall what I said in the previous lecture, now we want to think about the system, which is driven as a source of radiation, and then it radiates at some later time, okay? And so that's what's displayed here, this kind of ringing down. Now, this I've shown here, 1, 2, 3 pulses perturbing the system. In reality, we actually use 2 pulses, and so I can imagine that I still need 3 powers of the field, and so I either use 2 powers of the first field and 1 of the second, or 1 of the first and 2 of the second. So some of these timescales here are collapsed. Yeah?
Is the plotted quantity the driving field or the resistance?
What, here, red is the driving field and black is the emitted field in this schematic. Yeah. Okay, so now what I've done here is I'm going to kind of run you through this, but I'm going to make a number of different perturbations that's my ground state density matrix. And I come in with a pulse, that's this impulse here. And what I'm going to do at every point here is I'm just retaining the perturbation. If I return the whole, if I retain in each of the steps, the full density matrix, it's just gonna be this huge, complicated, messy thing. So this is coming back to that guy here. I'm gonna imagine an impulse which creates a perturbation of the density matrix like that. And in my notation here, I'm just keeping the perturbation after every step, right? The rest of it actually turns out to matter. Okay, good. So what happens? I come in with a pulse. That's like the first one. That creates this perturbation of the density matrix. Some amount of time goes along and I allow time evolution of the density matrix. That's T1. That's the T1 there, corresponds to this T1. It's a perturbation that exists in that upper quadrant of the density matrix. I can come in with another pulse, creates another time evolution of the density matrix. And you can see the off-diagonal parts. If you're familiar with some of the notation in magnetic resonance, you can see the off-diagonal parts are time evolving with a exponential, with a T2, and the diagonal part here is this part of the diagonal is evolving with an exponential that has a T1 in it. These are two-level systems, so we can use all this T1, T2 language that's familiar to us in NMR, come in with a third pulse so that the density matrix time evolved. And then at a fourth time, there'll be another interaction with the field, and that's the radiated field, and that's what I'm left. Now, this is just, as I mentioned, there are a lot of different possibilities here. They're different, basically, if you can imagine, the perturbations, the density matrix can kind of appear at different places here. And where the perturbation appears corresponds to one of those kind of trajectories of making different ultimate, measuring the different responses that appeared at different places on the 2D plot, right? So each of those different places on the 2D plot, the things that I told you about, rephasing response, non-rephasing response, pump probe, the two quantum wouldn't be on this because there's no two quanta in a two-level system, but nevertheless, those different places in the spectral plot correspond to different patterns of perturbations of the density matrix. Okay, so in the end, we come up with this expression here, and this is, that's for one of the parts, there's a real part and imaginary part, and this guy here, which in our literature we refer to as R1, is the so-called rephasing response. And you can see it appears in here for this two-level system, a T1 and a T2 time. Okay, yeah, there's some other details of that, but let me just kind of skip it and start going to some examples. I don't know if there's any questions about that before I go on. Yeah. You learn, so I'll get to that, but what you can learn from this is the T2 time, ultimately. This is written in the time domain, and the T1 time, okay? This is for a two-level system, right? I mean, the resonance frequency, the T1 and T2 times, that's about all there is, but for a two-level system. But if you have if you have a number of different states in there, then of course the density matrix is more complicated. The output is more complicated, but you can kind of make sense of it in this way. Yeah.
But in order to maintain the perturbative wave, what has to be done? Is there any time scale or energy scale should be smaller than something? How can we?
Well, so the electric fields need to be small, such that there is, well, okay. So I mean, if you go back to here, if I operate this thing on that density matrix, time evolving it in this particular fashion, I will at epsilon is the field. At second order, I will develop a contribution in the other part of this. This entry in the density matrix. And so to be in the perturbative scheme, the off-diagonal parts have to be much smaller than the new part that I introduced there along the diagonal of the density matrix. The electric field, to answer it simply, the electric field needs to be small. Yeah. And it's time, if it's a delta function, it's one thing, but this integrated quantity needs to be small. That's the better way of saying it. Right. So in conventional NMR, people will speak of a language where they're thinking about they have a block vector, and they'll have a pi/2 pulse, pi pulse. There's such a thing as the Hahn echo. That's not a perturbative language, right? But that's what we use here generally for understanding things here, right? So there are parts of this which correspond to echoes, but we wouldn't understand them in terms of like a Hahn sequence, for instance. Yeah. Next slide, yeah. Yeah, there's some, I mean, it's not a big effect if the resonances are narrow, right? So this is still called if there's a finite width, of course, that does contribute to some kind of bandwidth, but it generally is not a big effect. If you take the Fourier transform of this, that's generally going to be could be much wider than any particular resonance, and then maybe there's a small intensity modulation, but it's not a big deal. This could be it could come into some of the other analysis later on. Yeah. Sometimes we'll do experiments which are different than these, where we will use almost a monochromatic pulse. Not quite, because it does have some time length. Yeah. Because so what you can see is okay, maybe it's best shown graphically here. So if I have 3 pulses, then I can end up, so this is what we call the frequency vector scheme. In a frequency vector scheme, I don't know where here, one of the we have 2 different kinds of vectors. If we had 3 vectors, I don't know how the frequency vector scheme would exactly work, but what you can imagine is there are more places that you can kind of end up on this plot, right? And we don't generally, we can learn enough information. 2 is simpler than 3 to do the experiment. And we can generally end up at places on this plot which give us information. We can, let's put it like this, we can end up at a lot of different places on this plot just using these, this vector, it's minus, and this vector, and it's minus. There are other experiments that you might want to do, and we're thinking about doing them. And one particular, with a 3-pulse experiment, you can measure something which might be very useful for disordered systems, which is called spectral diffusion. So that's something that the chemists do a lot if they're thinking about like maybe some vibration in a molecule, and this molecule is in, I don't know, something that the chemists, I don't know, like water, and its vibration is changing as a function of time. And so you can imagine if you have a sharp oscillator and you measure its spectral line, but the oscillation frequency is changing as a function of time, it's spectrally diffusing, that could lead to a broadening. That is not representative of a line width. And so that's the kind of thing you can measure with 3-pulse experiments. Yeah. But we want to do that, we just haven't done it yet. For the things that we want to do, this is enough. And as Will can tell you, it's already complicated. Yeah. Okay, good. Will instead. Yeah, okay, good. Okay. Oh, I don't want to go through all this again. Let's go on there. Okay, good. So let's give some examples. Okay, so the first example then, so what can we do this? We can, let's look at a spin system with coupled magnons. So this is not from my group, this is from a collaboration with Eduardo Baldini and Keith Nelson, but is nice. So this is in a material, it's a classical, it's a ferrimagnet, it's almost an antiferromagnet where the spins are pointing in 2 different directions on some lattice, but then there's a little bit of canting. So it's an antiferromagnet with some canting, and there's some that, in fact, that's what's shown right there, kind of exaggerated with the angles. And there's, as a result of this canting, there's 2 different modes here, which are essentially magnon-esque modes that are referred to as the antiferromagnetic mode and the ferromagnetic mode. They have different frequencies. Oh, sorry, ferromagnetic and antiferromagnetic. And they have different frequencies. You can select them by polarization, right? And so that's what's shown here. If this crystal is oriented with its net magnetization, let's say in plane, and we polarize the light perpendicular to that, I can excite this set of resonances here, okay, which are at, let's say, some frequency of order about 300 gigahertz. If I take the sample and I turn it by 90 degrees, so this is not a sample with C4 symmetry, I turn it by 90 degrees, then I can excite the different set of resonances, right, which are different frequencies. So one of these guys, and I don't remember now, one of them is at 0.3 gigahertz, and the other is at about, 0.3 terahertz, and the other is at 0.6 gigahertz, something like that, and I can excite one or the other. You can see that there are some of these peaks that we've already discussed. There's the non-rephasing peak, there's the rephasing peak. That's the 2 quantum signal right there. So that accounts for exciting 2 magnons at a time. If you had really narrow line widths and perhaps a situation maybe with non-collinear spins in a system like this that were even more pronounced, you might see that that frequency of this guy was displaced from the ones below, which would correspond to the hardcore interaction of 2 magnons, which is a very interesting thing to measure. I mean, you can't measure it in any other way, right? The interaction of 2 magnons. So this is one set of magnons. That's the other set of magnons. And now you've come in, you put the sample at, I don't know, 45 degrees, and you can excite both. And what you see here is this pattern is not just the sum of this one and that one. There are new peaks which appear off the diagonals in the fashion that we just talked about, right? And so what are those? Those represent this kind of coupling between one set of magnons and the other. And so it means I can drive one and then influence the other one. And so this is the first detection of this kind of nonlinear magnetics, and there's proposals for using this for some kind of spintronics applications. I think it's just kind of interesting.
So the like lines of amplitude connecting the different peaks is
The
that.
streaks, you mean?
Yeah.
Yeah, so what that comes from is kind of a technical artifact that exists in the data now. I made a big deal talking about real and imaginary complex response functions. In this data, as it exists now, we've been thinking about it, but nobody has been able to, in a good way, discriminate the real and imaginary parts. So you can imagine that. And so what's plotted in this data is just the magnitude. And so generally, right, so if I have some oscillator with a sharp spectral response, maybe delta function, let's say, that's its dissipative response. Its non-dissipative response is this. And if I just plot the absolute value of this whole thing, what do you see? You'll see something which is like that. It's peaked at the right place, but then has these kind of, streaks that come out in either direction. So that's what that's coming for. Yeah. Okay, good. Good. So let me show you what I got interested in as first. And so it was actually our first paper on the topic. It was a theory paper. I actually started thinking about this. Be a very good paper in physics today by Steve Cundiff, who was a professor here and was at NIST and Gilla for many years. Now is at the University of Michigan. They was a kind of supposed to be a pop piece on what you could do with two-dimensional coherent spectroscopy, not in the terahertz range. It seemed very significant. This was an important technique. I couldn't understand what these guys were talking about. It was all done again from this physical chemistry literature where they have different names for things. You have to kind of learn the jargon, and then it became much easier. In that timescale, and as a way basically of trying to understand what we might do with this, I started thinking about what might be the unique application for this. And in fact, now I think there's a lot of things to be done. But at the time, I kind of thought the killer app might be this. And so one of the things, of course, many of us are interested in is frustrated magnets and perhaps quantum spin liquid systems, right? Where we can think that a system which has antiferromagnetic interactions, this third spin, which can satisfy bonds with none of the neighbors, can relieve this frustration in one of a number of ways, but one possibility would be to create a state like this, right? Where we have singlets formed on these lozenge-shaped bonds, and the ground state is a macroscopic massive superposition of all possibilities of the way you can tile the lattice with one of these singlets. Now, it's kind of a cartoon for what you would get in a neutron scattering experiment, or for that matter, a terahertz experiment. This is showing a neutron coming in, but you could imagine a very similar thing coming in with a photon. This neutron could come in and hit one of these singlets and break it up. So it was a singlet, it was spin 0, and now there's two spin 1.5 particles here. And so this excitation, you went from spin 0 to spin 1, right? That makes sense. This neutron, which is spin 1/2, flips its spin as it goes out and goes away and deposits spin 1 in the lattice. But you can convince yourself that what happens now is that these two guys can kind of propagate independently from each other. And this is a cartoon of what happens with spin-ons. Right? So one particle comes in and creates two particles behind, which can separately conserve energy and momentum. And the result of that is in neutron scattering spectra and terahertz spectroscopy for that matter, big, broad continua that hide any interesting information in them typically, right? So this is some data from some number of years ago on a material that was a hot topic at the time. I've done some work on this material as well. This is not my data. Ytterbium manganese gallium 04. It's a triangular lattice system with antiferromagnetic interactions. And one of the things that was noticed in the neutron scattering spectrum is this is a plot of the neutron spectrum as a function of momentum. The spectral response is plotted out of the page, and you see no sharp peaks. If this was a well-ordered magnet, you would see these kind of like sharp dispersive features, which correspond to magnon modes propagating through the system, which, but you don't see that at all. You see these big broad blobs, okay? And this is cuts through momentum, cuts in momentum space at different energies as you kind of come up. And again, no sharp features. There's some kind of, there's a spectral response, which is not completely flat, but nevertheless, there's not a whole lot of information here. This material was proposed in this paper to be an example of a system with a neutral Fermi surface. The problem is that in the system, manganese and gallium have about the same ionic size, and they substitute for each other, basically at almost the complete utter substitution, which incredibly disorders the crystal field environment for ytterbium. And so this system is just disordered like heck. And this is, it turns out to be a rather unfortunate repeating theme in the field of searches for quantum spin liquids, is that systems that we're interested in, which may be good candidates for this interesting physics, turn out to have other problems which allow us not to understand what's going on. So this spectrum are big and broad. Well, what would you have if you had a magnet which had just gobs of disorder in it? Well, the spectrum would be all washed out. So it's a rather unsatisfying state of affairs. You either have this super duper interesting thing, a neutral Fermi surface, or you just have junk. And they appear in the spectrum in the same way. And so, again, rather unsatisfying state of affairs where the coolest thing ever and the worst thing ever are actually appearing in your experiment as the same thing. Another example of what you might get here. So this is actually even simpler example. This is of a ferromagnetic chain. Again, the real situation is more complicated, but this is a cartoon of it. Imagine, again, a neutron coming in, flipping a spin in a ferromagnetic chain. And we can imagine now there's these kind of, if you will, emergent particles, which are not the spins themselves, but are these domain walls. But you could imagine them moving apart from each other separately in this fashion. And again, this is an example of fractionalization of particle, what would be a well-defined spin one particle in a well-ordered magnet. Okay. This is a system we've actually done an example of that. The best material realization of this is cobalt niobate. And this is a plot of our terahertz spectrum as a function of frequency. And we see this kind of big, broad blob here with some features. And although these may look sharp to you, and in fact, these correspond, basically it looks almost like this part of it in blue looks like the density of states in one dimension. And so this is again corresponding to the continua of two domain walls. A neutron comes in, deposits energy and momentum in the crystal, goes out, and that energy and momentum can be shared into the two particles, if you will, in different ways. And so there's no sharp features.
This is a ferromagnet that you draw.
This is a.
Separate those, you're increasing the spin.
I
think you meant to draw an anti-ferromagnet.
No, I meant to draw a ferromagnet. So this would be This is simulating essentially Ising model and transverse field. So spin is not a conserved quantity in such a situation, right? So imagine a Ising model and transverse field, some distance to the critical point, right? So these domain walls get kinetic energy because of the transverse field. You could draw an anti-ferromagnet, which if it was Ising would have the same problem basically. But ultimately we usually think about these systems being, the thing that I didn't get into the details, the thing I want people to think about if they want a model is the Ising model and transverse field, which is in fact what we ended up doing calculation for. Okay, good, so that's the issue. Big broad spectrum. It's a rather, again, unsatisfying state of affairs when we're looking for these interesting exotic states of matter, and we say that the proof of them is the absence of interesting features. Right? So what can we do? So this is a paper we wrote some years ago, which is we took the simplest possible model for fractionalization, and this is just what I had mentioned to Steve. It's a bunch of ferromagnetic spins interacting with each other by nearest neighbor exchanges, subject to a transverse field. Okay, so this system is it's kind of a paradigm for quantum criticality when H and J are equal to each other. There's a phase transition to what's called the high field state or spin polarized state or quantum disordered state by different names. This data here is all in the ferromagnetic regime with some small but non-zero value for the transverse magnetic field. What I plotted here is the real and imaginary parts of the susceptibility, right? So that's the dissipative part of the susceptibility. Again, back to this theme of real and imaginary responses for things. This broad blob here is the continuum response for these two domain walls. Okay, so this is a model which is integrable, and so the excitations in the system are actually eigenstates, so they don't decay. They have infinitely long lifetimes. So the fact that you see this big broad blob here, what you're seeing is this kind of superposition of delta functions. Right? You don't see any sharp features again because you can deposit. We're exciting the system at zero momentum, but there are many different k minus k pairs at different higher energies, if you will, that can be exciting. When we look at the 2D response, that's plotted here, and this looks very similar to even the cartoon that I showed you before, right? It's plotted in the fourth quadrant, not the first quadrant, but you see this streak here, and that's essentially the streak of delta functions. So if you understood those cartoon I gave you of the pendula, this is essentially exactly the same thing from a spectroscopic perspective. A cut in the off-diagonal direction is here. It's a delta function, negative for reasons. There was some convention we introduced in this paper. Now what we did here is the real model is integrable. So what we did here is we just by hand introduced T1 and T2 times. You either have this domain well excited or you don't. So that's a two-level system. And so just in the equations of motion, we just put in T1 and T2 times, and you can compare this to that. And what you can see is there's a little bit of broadening on the edges, right? So now there's if you will, spin on decay. You go from here to there, and you can see, yeah, it's a little bit broader on the edges. These peaks are not quite as sharp as they were anymore. But you would never believe me if I told you, I could measure really something that would have looked like that, and it actually looks like this. And from that, I'm trying to extract a lifetime. But in the nonlinear response, it's night and day, right? The streak of delta functions is now broadened out. Now, this here is a calculation where there's no decay put in, but the couplings, J and H, are all taken from an ensemble of some disordered ensemble. That model is still integrable. And so you see, again, you get some broadening. You would never be able to tell the difference between this guy and that guy. That's broadened because of decay. That's broadened because of disorder. But in the nonlinear response, it's very different. You still have the streak of delta functions. There's some little bit more structure, but the main bit of the spectral weight is in this sharp delta function that's right there. So that's the essential idea behind looking at this. Yeah. Eta, where's Eta? Oh, yeah, let's see. I don't remember the details now. I mean, this is basically, it's periodic boundary conditions. So that's something I think, what did we do? Maybe we put a twist in the boundary conditions. I can't quite remember.
Like red features in the spin-on decay case in Fortin et al, or that's just.
So no, they're not particularly important. So they're positive and negative regions. And basically what you're seeing there, this is not experiment, this is theory. So we have no problems measuring the phase. And so you're seeing the positive parts. That's the dissipated part of the signal. And that's the non-dissipated part. So you're seeing basically that peak there positive and that peak there negative. Yeah. Yeah. What's the question?
What's the temperature?
The temperature is zero temperature. Yeah, zero temperature. Yeah.
Maybe you said this, just to make sure I understand. What's the intuition for why putting in some decay?
What's the intuition for what was the last part of this?
Oh, second and third line.
Yeah.
To emphasize that disorder still preserves the delta function by just putting in some decay by hand.
Well, so yeah, I mean, Ising model and transverse field is it's an integrable model. Still, disorder doesn't break the integrability. So, and I'm not an expert on this, but that's something that I know.
Disorder doesn't break it, but I see. So there's no K resolved. Is that K resolved?
It's K equals zero. I mean, it's K equals zero, right? It's the optical response at K equals zero. So in the non-disordered case, you're making these kind of K. You have this what almost looks like a tight binding band. And you're making this K minus K pair. At higher and higher energies, you kind of march up to higher and higher Ks, K minus Ks. That picture, of course, is not as relevant once you go to the disordered case. Yeah. But you get broadening, right? There's level broadening that happens. But
K-space states will be broadened.
Yeah.
Though there are some other exact.
Yeah. Yeah. So it's not transport experiment. I mean, that's one distinction that's made as well, right? So it's not you're really looking at the decay of these levels, which presumably get localized, on some long length scales, but don't decay. Yeah. Yeah. So that's interesting. So here, this was a 4-page PRL with 45 pages of supplemental because we were trying to establish a bunch of points of principle here. But ultimately, I told you about if you understood, I said you understood basically the main gist of it. Better than doing kind of by hand putting in decay here, which is what we did, go and break integrability in some fashion. And what that was done, I think, so there have been a number of different theory follow-ups, but the most important to this study was by Rahul Nandakishore, who's a professor here, I think out of town this week. And he went and put in next nearest neighbor couplings, which breaks integrability. He put in, what was the other field he put in? Anyway, some minimal coupling was that broke integrability and next nearest neighbor exchanges, which distort the spectrum enough that allow decays. And what you see there is this kind of really beautiful thing where you would have like, let's see, how am I going to draw it here? You will get in that case, how does it all work? I need to remind myself. So you have this like let's say, spin-on band, and then you're going to have the two spin-on continua. This is just in dispersions. When it enters the spin-on continua, see this broadening. What in the 2D response, let's say, let me draw it like this here in the third quadrant, you see that there is a sharp streak here, which is basically delta functions. And then you hit the two spin-on continua hitting, actually, sorry, the six spin-on continua, because that's the necessary constraint, and then you get this kind of broadening. So putting it on this feature here, in Rahul's calculation, you see this sharp streak, and then you hit the two spin-on continua at some high momenta overlaps with the bottom of the six spin-on continua, and you start to see broadening, which is kind of just what you'd expect. Okay, so this is what we're after, and it's something that we've been working on now. It turns out, so all of these couplings here of the terahertz magnetic field, the terahertz to these spins are going to be through magnetic couplings, right? So it's the time domain. We've been talking a lot about electric field responses, where terahertz or light would couple to systems through the electric dipole to lowest order, but you can also have other couplings. And here to these spins, presumably the coupling is from the time-varying magnetic field to the spins. That is much weaker generally. And so this has been hard for us to see. We are hot on tracks of this, but we haven't actually succeeded in seeing this yet. And I hope we made a bunch of changes, and I hope that this is some effort that Will's involved with, although his main project is elsewhere. And I hope that we're going to be in a position soon where one of these materials that are good examples, are good platforms for easy model and transverse field, like cobalt niobate, will yield basically be a kind of a model system for being able to look at spin-on decays. And if we can do it there in 1D systems where we kind of know the answer, if you will, then we hope to be able to export this to systems where we don't know the answer, which are nominal spin liquids. And there you would have like proof, positive proof for a spin liquid in some situations where you would be seeing broad features in the linear response, but the nonlinear response measured in the right fashion would show sharp features. And so that would be positive proof for a spin liquid. Okay. You may ask what happens if you go to even higher transverse magnetic fields. That's on the ferro side. If you know something about the easy model and transverse field, this is on the ferro side. That's the data I was just showing you. That's that streak I was discussing. If you go to high fields, then the excitations of the system are just spin flips. And so that's this kind of spin flip mode here on above the critical point. And that's its 2D response here and there, right? So it's just a sharp feature. This streak gets replaced by just dots. Very similar to the Magnon example I gave you a little while ago. Yeah.
Would it be easier to do terahertz on like an electrical 1D system, like a linear liquid that also has similar kinds of fractionalization in it?
It would be easier to couple to it, presumably, and see some nonlinearities. Those are systems with continua. They're metals, essentially. Something like conductors, let's say. And so Luttinger liquid, I wouldn't want to. So if I had some insulating version of this, like a liquid state which was insulating. I mean, once we start talking about zero frequency excitations, then these echoes go away. So it gets more complicated. I'm going to talk about metals a little bit. Yeah. Yeah. There have been some interesting predictions for what happens in Luttinger liquids. Okay, good. Let me give you some examples then for things which have worked for us so far. So the first thing we went after were some system which is near and dear to my heart, but maybe only my heart, maybe Steve's heart too, phosphorus doped silicon. Sentil probably. You guys all, of course, our resident glassy guy on the front row likes phosphorus doped silicon as well. Yeah. So phosphorus doped silicon is, we would imagine, an ensemble of a crystalline ensemble of silicon atoms, where something like 1 in every 10 to the 6 silicon atoms is replaced by phosphorus. Okay? So phosphorus has 5 valence electrons. 4 of those electrons go into making bonds with their neighbors, but 1 electron is left over, and that electron which is left over goes at low densities, when these things, every phosphorus is really far from each other, goes into some kind of quasi-hydrogenic orbital where it's kind of orbiting it around. The Bohr model, the Schrödinger equation would be some kind of rough guide to what the physics of that is. But when you start making this material at higher and higher densities, these hydrogenic orbitals start overlapping, And for about 1 phosphorus in 10 to the 5th silicon atoms, there's a collectivization which happens where you get a metal insulator transition, a 3-dimensional metal insulator transition, early example of a quantum phase transition, and something which, the metal is interesting, but the insulator is very interesting as well. And so something that I, kind of emphasize sometimes to gin up interest from people who might not be interested otherwise. If you're interested in strongly correlated systems, this system is probably the most strongly correlated system that you can imagine, right? There's long range 1/r Coulomb interaction. If I move, there's no metallic screening. So if I move one of these charges somewhere else, it has a 1/r Coulomb interaction, which influences the potential on every other site. So if you will, every potential site in the system is a function of all the other occupations. So that's interesting. It gives rise to glassy phenomena and a number of predictions that people have been interested for a long time about its physics. Now, one of the things that the reasons we went to it first is that one of the ways that we try to understand the system, particularly when it's dilute phosphorus atoms, is that it was first discussed by Mott that in the 1950s and 1960s, when he was thinking about problems like this, is that if you're thinking about low energy degrees of freedom, and particularly the optical conductivity, you can think about the degrees of freedom of the system not being these kind of individual localized charges in space here, but instead kind of an emergent network of dipoles. So we replace the strongly interacting 1/r Coulomb interaction, which is perhaps a reasonably dense ensemble of charges, with a sparse network of dipoles. Okay? Now we have these dipoles, so that's a 2-level system. And so this turns out to be quite useful for us as a kind of as a warm-up problem, because we have a 2-level system. And so I already told you, we already know how to solve the nonlinear response for 2-level systems. So that's what we were interested in. Now, kind of setting the stage, there's a lot that you can disagree with this, but I still like this quote from Phil Anderson from 1970, because it kind of sets the scale for some of our stage for some of our thinking here. It's from an old paper. Often people will refer to systems like this as Fermi glasses. And I'll read the quote to you. The Fermi liquid theorem, which we've heard a lot about so far in the school, is a rigorous consequence of the exclusion principle. It happens because the phase space available for real interactions decreases so rapidly as E squared or T squared, right? So we've been hearing about that this morning in Dmitry Maslow's talk. This is equally true for the localized case. At sufficiently low temperatures or frequencies, the non-interacting theory must be correct. Even though the interactions are not particularly small or short range, the electrons can form a Fermi glass. And so what Anderson was thinking about here was, like Fermi liquids, imagine a system who had kind of, despite all of the details and strong interactions, had some universal properties which were essentially mostly dominated by the Fermi statistics alone. And interactions were kind of something that came on top of it. But at low enough energy scales, you would expect to find maybe the microscopic wave functions very complicated, but nevertheless, a kind of emergent description in terms of what could be considered weakly interacting excitations. And so the question is that right? And there's a number of reasons to think why this is not right, but I'll show you experimentally is that that's not right. Yeah.
The previous slide, those unoccupied state of the dipole, those are the excited state of this hypergenic bound state, or
No, so those would be, you would be considering that you would have some states in the system which are occupied and some states which are unoccupied.
those are not phosphorus atoms.
Those are phosphorus atoms which have been ionized. Yeah, so what happens is, and a very small chance that it could get ionized, put an electron on donor. Once you start getting enough of them, there start to be overlap with the wave functions, and now you get clusters. And some of those clusters ionize. And when they ionize, so they become, there's some clusters just through rare events that we've heard about, rare regions, it becomes energetically favorable for them to accept an electron from another cluster, and that opens up space. So that's generally what's considered that happens. And so I've glossed over a lot of that here, and at the details of my understanding, I don't think that, that's not coming into it a whole lot. You should just think you have a random ensemble of some filled states and some other states which are unoccupied above the Fermi.
Peter,
Yeah.
on the statements, you have to, in order to falsify them, you have to define what you mean by theorem and what you mean by true.
Yes. Yes, yeah, that's right. Yeah, where does it say here? It does say theorem, right? Fermi liquid theorem, yeah, that's, maybe I should spare Phil the Fermi liquid, and then I can put in parentheses, notion. Yeah, concept.
His definition of theorem is things that he believes to be true.
Yeah, okay.
Things.
Yeah. So, yeah, maybe I'll edit it to say notion, but at any rate, the point is, I use this to set the stage, but the point is that we want to understand whether or not there are some low energy excitations in the system which can be considered to be well defined. So this is data you've seen already. Yeah.
So the clusters of silicon do have this phenomenon where local moments in the state.
Yeah.
So that's obviously
Right.
totally normalized.
Yeah.
to a free-
Yeah, so that was one of the things I was kind of alluding to, was whether or not there are a lot of things that you can say about why this is naive, but I think still the question is valid about whether you're doing AC conductivity experiment. Can you at low energy scale see excitations which are have line widths which are narrower than their energies themselves? Yeah. But if not, then let's talk about it. Yeah, it's not obvious to me that that's not a good question to ask.
So like
Yeah.
spin excitation higher than S.
The spin excitations?
So these Docklets have.
Yeah, they also have spins. Yeah, so I'm not sure exactly how that comes into the story here, but in terms of the excited states of the system, we are overwhelmingly coupling to the electric degrees of freedom. And so there are spins that are there, that's for certain the case. But generally speaking, if you have electric dipole and a magnetic dipole, they're sitting right next to each other, in kind of making some rough estimates for this, the electric dipole will be stronger by essentially 2 inverse powers of the fine structure constant. So you're talking about stronger by a factor of 10 to the 4th, almost 10 to the 5th. So if there's magnetic stuff there, you won't see it. In magnetic insulators, like that cobalt niobate that I showed you, I showed this plot with this kind of 2-peak structure, which I said was like a 1D density of states. So that's a material which is an electrical insulator with a band gap of 3 electron volts. And so there, it's a thick sample that we have weakly interacting spins, weakly interacting with the magnetic field of the teratibles. So it could be that magnetic physics, magnetic spin physics is interesting here, but again, it didn't. I don't see where it comes in, but I'm happy to have that discussion. Let's look at the data. Okay, so this is data you've seen already, and A, B together, and then the difference. We're looking at the Fourier transform of these things. And so this is something that you're now adept at reading on these plots. I didn't give you all the details, but one of the things that you remember for these 2-dimensional plots is different regions on this plot correspond to different responses. And by taking cuts in different directions, it's something I didn't mention, and it doesn't unfortunately come out very well on this plot here, but there are peaks in here, and by taking an anti-diagonal cut in this way, we can center in on the T2 response. And so the width in this direction, if I think of this as an ensemble of 2-level systems, then it's 1 over T2. And if I take a cut that way, it's 1 over T1. Okay, that's just something that comes out from that kind of considerations that we talked about when we were talking about this perturbative scheme of the density matrices. And that's slices this way, slices that way, this anti-diagonal cut, that's a spectrum right there, right? So there's from the green region here, 1 over T1, and from the purple region here, 1 over T2. Right, and there's differences between them. We can, something we can do here now is we can imagine taking slices, kind of moving along the diagonal here, these anti-diagonal slices, and then essentially looking at these rates as a function of the excitation energy. And when you do that, that's plotted here. You get these 2 rates, and you can see on this plot here, this dashed line is unity. And so you get these rates here, which are scaling linearly in energy with a coefficient slightly below, but very close to 1. So, coming back to the Anderson idea, who wanted to think about a Fermi glass, we refer to this thing as a marginal Fermi glass because relaxation rates going linear in frequency is similar to what is seen in the cuprate superconductors in the context of the Fermi liquid phenomenology. And so in homage to all of these things, we called this a marginal Fermi glass. And so if you could continue these lines down to low energies, the takeaway point is that there is no region at low energies where the system has some collective or some low energy excitations, which are essentially have line widths, which are just smaller than their energies themselves. So the system is essentially always strongly interacting. And then another takeaway point from this is the phosphorus doped silicon is not, if you will, mappable to something like an Anderson insulator. Yeah.
So the fact that the rate goes to 0 at the figure, is it a signature of this Coulomb gap?
No, not directly. Yeah, no, Coulomb gap is something a little bit different that would have to do. The role of the Coulomb gap in an AC conductivity experiment, I think, would be controversial. So Coulomb gap is something that basically you would see in the n+1 or n-1 spectral functions, right? So in the electron addition or removal spectrum, and not in an optical response. Yeah. So it's a charging gap essentially, right? It's response to taking charge out of the system and the energy cost that it takes to beat the long-range Coulomb interaction. Okay, yeah.
So I'm just using the analogy to NMR, T1 and T2,
Mhm.
but these are all the electric dipoles response upon the light of the terahertz light, right?
Yep.
So can I think about also T1 and T2 as a kind of separate T1 and some more like, including some environment or lattice information as well versus T2 is purely their own correlation or something, how can I interpret this, as an outsider, how can I interpret this?
Yeah, so they also have interesting temperature dependences. So the 1 over T1 basically has no temperature dependence up to about 30 Kelvin, whereas 1 over the T2 does. So the temperature dependence is also such that these lines actually get a little bit narrower as you go up in temperature, right? So this is also an unusual thing. From that observation, we ruled out that the principal effect of this broadening was not lattice interactions. So phonons basically coming along. So this was a collab, I mentioned him before, but Rahul Nandakishore was a collaborator on this project from early stages. We also were fortunate to work with because the line widths decrease as you warm up. Yeah. So the model that Rahul and Sarang Gopalakrishnan put together was essentially one based on dipoles interacting with each other by dipolar interaction. And there's an old model that goes back to Levertov about how dipoles, basically delocalization of dipoles on a random lattice. And so that was the model that was basically used. It turns out when you put in for the density of states for the dipole density of states in the system that we think exists here. There's a lot of technical details in all of this that have to do with corrections to the density of states, the things that Efros and Shklovsky talked about. Let me not explain all of those things, but just say that there's a theory for accounting them. When you take the Levertov theory and account for what we think the density of states of the dipoles are, linear in omega is what comes out. It's basically the delocalization rate of a dipole. So I have a dipole here, so maybe this cuts to the chase. I have a dipole here, and it can, via dipolar interactions, talk to a dipole there, and it basically its energy can delocalize through these interactions. And so that's the essential. Pure dipolar interactions, and basically what you're sensitive to in this is essentially energy diffusion of the dipole you've excited. That's a good question. It's not something we considered. We considered delocalization of the dipoles energy through this random ensemble of dipoles.
Not exactly the same energy.
Yeah, so that's why the linear in omega comes in. So that linear in omega factor is basically the scaling. So dipolar interaction goes like 1 over R3, so it goes like 1 over volume. And so the scaling of how you would expect the number of dipoles within a volume goes is exactly right, basically to make it marginal for the number. You expect basically to find one dipole within the right distance to basically be resonant with it. Yeah, so the dipoles have to be the right energy to get this kind of resonant effect, but the scaling works out because the dipolar interaction goes like 1 over volume. There's another factor of omega which comes in because this is some dynamic quantity. Yeah, so it's
So this is a 3D.
This is a 3D material. Well, I don't know what you're supposed to see or would see, but we didn't do that experiment. Is there any reason to think, well, the power law should be different because, yeah, because it doesn't go like 1 over volume then, it goes like 1 over area, but the dipoles are still interacting with each other as 1 over r to the third. Yeah, I don't know. I mean, this argument also depends upon the energy scaling of the density of dipoles, which is also depending on the dimensionality of the system. So I know if you had like the density of dipoles that Mott used, then you would actually expect this rate goes like omega squared. So yeah. I should say, let me just say before I say that though, because I was touting the theory, those guys even explicitly in our paper said that their theory they have this theory, but it probably explicitly doesn't apply because this theory is for resonant dipoles is in the dilute limit. We're not in the dilute limit. So they can figure out that things in the dilute limit go like omega, but this is with a coefficient close to 1. There's no theory for the prefactor. And it's certainly not explicitly valid this close to the metal insulator transition. Yeah, please. Yeah. I don't know what you mean by comparing it to. Yeah, does not. Yeah, yeah. In this system? Well, yeah. So I don't know. You know what I guess is that this is. I mean, things like weakly interacting Anderson insulators or Anderson insulators, they provide us perhaps a cartoon for understanding the physics. Disorder is important, which influences localization. But you know, the model that I have, what's going on here, and I think this is ripe for a lot more theoretical thinking on the problem, is again that we have the elementary excitations or these localized dipoles, and those dipoles can lose energy, and basically the energy can diffuse and move out through the lattice, basically through this resonant dipole coupling. And so what is that thing that is there in the end? Well, it's kind of an overdamped version of what it already was a dipole. Yeah. There are other possibilities for things here, and I don't see how they're relevant. I don't know that they're relevant, but there's what Senthil had mentioned about these random singlet phases. And there's been interesting predictions for what happens with those systems in terms of fractionalization in one dimension. I don't see how that's relevant to higher dimensional system here, but you know, there's certainly lots. There's far more we don't know than we know, and you know, we did the experiment. So, okay, good. Other questions? Good. So let me go on to some final examples now, and this is thinking about kind of shifting gears to. All of that was about finite frequency excitations, right? So we had those magnons, which were at distinct frequencies. There were two kinds of magnons, and we could drive both at the same time, and then we could see these off-diagonal peaks, and they could couple to each other, but they were at finite frequency. We had these two-level systems, which were in the spin-on case, right? This domain walls that were there. We had a disordered ensemble of electric dipoles in the electronic glass. Everything's at finite frequency. So let's think about metals now. So here, we're going to think about metals as basically zero-frequency oscillators. So we talked about those different responses before, and the pump probe response, the rephasing response. Rephasing response is like an echo, right? A spin echo or a photon echo, if you're familiar with the language. And so for a zero frequency response, there's no echoes. And so, I mean, there could be in an interacting metal, there could be more complicated things going on, but certainly in the simplest picture, the way we should think about this is an ensemble of zero frequency oscillators, okay? Of course, there are going to be other considerations that come in from things like momentum conservation, et cetera. No, that's fine. Yeah. Okay, so one of the things that we're interested in, of course, is Coop rates, and I've shown you this slide, maybe the third time now I've showed you it. Resistivity versus temperature, all the way linear, all the way up to the melting temperature here. This is the linear optical conductivity of lanthanum, strontium, copper oxide, right? The real part of the linear optical conductivity. We're interested in the width of this feature. This is a plot of this rate as a function of temperature, and by the rate, I mean the width of this peak. It is, even if there's no quasi-particles in the system, it is still, if it has a well-defined width, this rate can still, I'm calling it momentum relaxation, but it can be formally identified with the rate of current relaxation, right? So we have an electric field, we drive a current, even though there's no quasi-particles, this rate still has well-defined meaning. If you want starting to think of that your current is made of little reasonably well-defined objects there, we can talk about the rate that they lose momentum. And if the system is sufficiently isotropic, then it's a momentum relaxation rate, which is the language that I'll use. Okay, so let me tell you about something first you know, and then I will tell you about something you presumably don't know. Okay, so first, this is kind of like a time domain version of what we do in an optical conductivity experiment. Imagine that's my Fermi surface, and I'm going to come in with a pulse, and I'm going to kind of Cattell level physics here, and I take the Fermi surface and I shift it sideways, right? I have now occupied these states here, and I've deoccupied these states. And one way of thinking about this is as a P wave-like deformation of the Fermi surface. energies, right? Positive here, negative there. In a crystal that has C4 symmetry, D4H for the cuprates, we might call this an E1U distortion of the Fermi surface. But this is a state with finite momentum. And so for this kind of distortion to go away, the electrons have to couple to something that can remove momentum from it, right? Which is why we call it the momentum relaxation rate. But it'll relax with a certain rate. And this is kind of, if you will, a time domain version of doing an optical conductivity experiment, where we could imagine perturbing the Fermi surface and then watching as it kind of comes back to the origin, presumably with some kind of exponential form, right? In reality, we don't do this. We take the Fermi surface and we're rocking it back and forth and seeing what's in phase and out of phase as we're doing it. But a time domain version of it would be exactly that. Okay, so that's something you presumably knew or now know. Okay, in contrast, imagine coming in with multiple pulses, where we're going to take the Fermi surface, if you will, and do this with it, rock it back and forth. And in the process of that, you can imagine if there's some scattering, the end result could be to leave some quasi-particles high at finite momentum, but on this side and that side, right? So I'm taking my Fermi surface and I'm shaking it back and forth. This is the perturbation here, is a perturbation that goes like the electric field squared. And if it's polarized, it goes like E cosine theta squared. And this thing, we can just multiply it out. And so it's E squared times this. And so there is a uniform part, and then this cosine 2 theta part. And we can think of this as the S wave part, and that is the D wave part. Or again, in the language of cubic harmonics, this is the A1G and the B1G. Yes. No, I just want you to think like that I've excited that this region here is kind of excited, and now the Fermi distribution is kind of smeared in those directions, right? So it's not really the right language, but you can kind of think it's like it's hotter here and there than it is there, right? But if I do this fast, I'm not going to do anything to the quasi-particles there and there, but I'm going to do something to them to the here, right? Because I'm moving them back and forth, they can scatter, and I can move them, and then they can scatter to the other side. If I had no scattering, and I do this, and I come back to zero, I'll just put all the quasi-particles back where they were. But if I have some scattering, then this is the pattern that I'll get. If the perturbation is fast. Okay, good. All right, so then that deformation, oh yeah, right. And so this can relax also. We can imagine that relaxing. And now I had mentioned, right, that we can think of this deformation here and there, where I've kind of left these guys high, as a superposition of, if you recall, right, it's 1 plus cosine 2 theta. And so that's the S wave part, the one, that's the cosine 2 theta, that's the B1G part. And so I can now imagine that I would be able to watch these guys relax. This here is a state of finite energy. It's not a state of finite momentum. It's going to lose energy through processes which allow the electrons to lose energy, but it doesn't care about losing momentum. This process here, this deformation here, is neither one of finite momentum or, to linear order, not one of finite energy, right? I've excited these guys here and there, and, if you will, de-excited here and there. And you can imagine, let's add up the plus signs, plus, minus, gives me 0, plus, gives me 2 plus there, right? So that's the intuition that comes out of this. So this is associated, this will decay as the system loses energy. That's an energy relaxation rate. And this is, if you will, we can call it different things. We could call it the D wave deformation. It's a B1G deformation, or you could call it the quadrupolar relaxation rate. So this is the kind of stuff that we can access with our nonlinear Territz experiment, which is just completely, it's important, but it's just completely invisible to conventional transport. What do we know? Let's take a simple case of electron-phonon coupling, right? So I'm going to take electrons coupled to phonons. The momentum relaxation, which is what appears in the resistivity, in the simplest case, momentum relaxation versus temperature, will give me a T to the 5th at the lowest temperatures. And then it will cross over to what we refer to as the elastic phonon regime. Dmitry Maslov was talking about this a little bit, where it goes linear in temperature. We say elastic phonon regime because this is at temperatures found, let's say, above the Debye temperature, above the Bloch-Gruneisen temperature. Basically, the electronic energies are much larger than the phonon energies. And so the phonons they're excited, but they're there, but essentially their energy scales are small. And so we can think of them looking kind of like elastic scattering impurities, so elastic phonon regime. If an electron scatters off of one of these phonons, it can lose momentum, but it's generally not losing much energy or giving up much energy or accepting much energy because, again, the energies just the electronic energies are far above the phonon energies. The energy relaxation rate, there haven't been many calculations of this, but this was first done that I'm aware of in this form in Phil Allen in the paper in 1987, although Dmitry told me that there's precedence to this in some of the old Russian literature where people were thinking about dephasing rates. But at any rate, in the form that appears in Allen's paper, one expects the energy relaxation rate as a function of temperature goes like t to the third at low temperatures and has a peak the same place where the momentum rate crosses over from t to the fifth to t, and then shows a peak and then goes down. This is the elastic phonon regime. And again, once you get to high temperatures, the phonons can't take away energy from the electronic system anymore, or at least it's a very small fraction of that, right? So one of the things we're interested in this here, oh, and there was one other point, this t to the third at the lowest temperatures here, this has a coefficient basically identical to what the electron phonon contribution to the electronic self energy is at the low energy scales. But then they start to differ from each other in that much. So that's the expectation. Okay. So what do we see? Again, this is optical conductivity. You've seen a lot of this. Your experts are looking at this now. The width, this is the optical conductivity as a function of frequency measured with linear response. That's the Drude model that I keep going on and on about here. That's the width of this feature that I want to identify with the momentum relaxation rate. Okay. This is a plot here of the signal that we're measuring in the two-dimensional terahertz experiment. It's actually measured in a slightly different fashion because we believe the principal contribution to the metal in the nonlinear response is this pump probe response. We can do a much simpler experiment where we scan instead of scanning the detection time, we basically scan the time between the pump and the time that we detect. Okay. And that's what this is done here. And it actually is done nicely and even analyzed nicely in the time domain. So these are data, again, on LSCO. This is a bunch of different temperatures. And so this is at some high temperature here. This is at a lower temperature. That's at a even lower temperature. And so what we're interested in here is this kind of relaxation dependence here. Here we expect Lorentzian form, and here we expect this exponential form. Of course, the Fourier transform of the exponential is the Lorentzian. Yeah.
How do you separate the quadrupolar part of this?
Yeah. So I glossed over this. So in fact, what we're mostly interested in, and this is what Will has been working really hard on for 2 years, told me yesterday. I didn't hear the news today yet, but I suppose I would know if there was good news. The B1G response, this quadrupolar part, is really hard to see. And so the way you see it, the way you separate it in principle is by doing polarization experiments. So I put up this kind of D wave, positive lobes, negative lobes here. So we do an experiment. We're actually doing an experiment a little differently, but it could be done in this fashion. You do an experiment where you basically make that deformation with X polarized light, and then you measure with X polarized light, and then you come back and you do another experiment with Y polarized light, but measure with X polarized light. The symmetric combination of these gives you the A1G response, and the anti-symmetric combination of these, subtracting them, gives you the B1G response. You could also imagine doing this protocol, but all at 45 degrees to get the B2G. The problem is so far when we do this subtraction, we're getting 0. I think that's just because this B1G response is really fast. And so we're not able to see it. There are all kinds of interesting questions about, we talk a lot about Planckian limits on the dissipation. We don't know. That's what's seen in the E1U channel, if you will, or the momentum relaxation channel. We don't know how fast this rate is in the B1G, right? So that would be a kind of, if Will finds it, then that would, and it's, much faster than Planckian limited, that's a very interesting point, takeaway point. Yeah.
So I'm just wondering if you go near a dramatic phase transition.
Yes. Yeah.
This B1G should be slow. Critical slowing down.
I think that the B1G will speed up in the electronic degrees of freedom. You don't think? Huh? Yeah, but you don't think scattering of the electronic degrees of freedom going off a soft pneumatic mode will?
As long as you have the soft pneumatic mode, the distorted Fermi surface is.
Yeah, it just stays there, right?
Yeah.
Yeah. So yes, so we're either when we see it in the coupe rates or we give up on the coupe rates. That's what we're going to. Yeah. Yeah, so that'll all be very interesting, right? It's an interesting thing to think about in general because this, this B1G, how does it, I like to think about how these Fermi surface deformations heal, if you will. So if I have excited at Kx and minus Kx, and I've got to put those quasi-particles to Ky and minus Ky, this dance, right, is the dance done by quasi-particles in a D-wave superconductor. So it may be also an interesting avenue for understanding the normal state interactions which lead us to D-wave superconductivity. There's a lot there. Yeah. Okay. All right, good. So yeah, so that's what data looks like in the 2D maps. If we take the full complement of data, right, with these frequencies, we're mostly going to be able to do this. You can see here, for instance, maybe it's most obvious, a little bit obvious there, this streak along the horizontal, that's the pump probe response. Interestingly, there is some kind of stuff out here off the horizontal, and that, you know, with our scheme that we understand should correspond to finite frequency excitations. That shouldn't exist in, you know, in a simple metal. And so there may be some interesting physics out in this rephasing and non-rephasing responses, but we just haven't thought about it yet. We're mostly concentrating on the pump probe response, which we can analyze in the time domain. And there's for a bunch of samples, 1, 2, 3, 4, underdoped, all the way up to overdoped. We've been very fortunate over the years to collaborate with Ivan Bozovic. He's given us lots of samples to work on. And so maybe too many samples sometimes. There, plotted is probably the thing that you're looking for. Plotted here, again, for that data that I just showed you, a number of different dopings as we work through the phase diagram for underdoped all the way up through optimal, through overdoped. Plotted in blue is the momentum relaxation rate, okay? Plotted in red is this energy relaxation rate, okay? And they're plotted on different scales, and there's a factor of 15 difference on the two sides here. So what you can see, though, in all cases is that the momentum relaxation rate is much faster than the energy relaxation rate. And, right, so this means the things which are taking momentum away from the electronic system, the scatterings that are not removing energy from the system. The other thing that you can find from this is that, well, this data here on the energy relaxation rate isn't quite clear, but over most of the range, the energy relaxation rate is an increasing function of temperature. Right? And remember the old Allen prediction, T to the third at low temperatures, and then a peak, and then it comes down at high temperatures. If we're in a regime where phonons are giving us linear and T resistivity, the energy relaxation should be a decreasing function of temperature. And that's just certainly what we don't see at all. You know, people ask me, you know, what is the power law in here? This data is unfortunately not high enough quality to be able to tell us what that power law is. That's Will's PhD thesis, one of the things.
But wait, but
Yeah.
the energy relaxation rate is much slower than the momentum.
Right. Yeah. Yeah. Is that what I said?
Yeah, you did, but that's a striking.
Yeah. Yeah.
observation.
Yeah. Oh, I should have paused for dramatic effect. You meant. Yeah. Yeah, I agree. Yeah.
Relaxing more or less elastic.
What's that? The energy. Yeah. So there's a number of. Things. Let me go to the next slide, and then. So what does it? So what does it mean? So what I think what it definitely means for the data is, again, the things that are removing momentum from the electronic, the scatterings that remove momentum from the system don't remove energy. What I think I'm almost sure it rules out is phonons as the source of linear and T resistivity. Now that may seem perhaps to this audience like maybe, you know, that's not saying very much, but you know, this is kind of, I think there's good reasons to think that that wasn't already true, but I think we've shown it, right? So we don't have to think it anymore. We've shown it now, which is a better situation altogether.
There isn't the peak.
It's an increase, yeah. It's an
Okay,
increase.
so suppose you have a broad distribution of phonons like Sankar's pose.
Maybe we need to calculate, yeah, but I think it's, I
I
don't,
mean, the even simpler thing is phonons would say that the energy relaxation rate is slow compared to the momentum relaxation.
so that's right, but I'm concentrating on the temperature dependence. So you would need to cook up some scheme where the temperature is, the energy dependence is still going up.
Sympathetic with the conclusion, but I'm not sure you can make it.
Yeah, okay, yeah. I mean, I think what one needs to model it, right? So you would need to understand how far could you distort the Debye spectrum of phonons?
It's not Planckian. If you wanted to determine that it's not Planckian, that would all
Yeah.
be everything the same rate.
Right, yeah, that's right, yeah. So you need to, I think, do a real calculation and to make it really definitive and see how far in the old Allen calculation, it assumes a Debye spectrum. So you need to see how much you could distort the Debye spectrum, which are wonderfully universal at the lowest energy scales, but who knows if that's where we're at. The other thing that I don't know if we rule out or not, and that is if it doesn't rule out the general picture of electrons coupled to some other collective mode, which is not phononic in origin. And here, I don't know, I think to me, there's an interesting theoretical issue. I try to get theorists interested in this idea. Does it make sense to think of some electronic collective mode and pick whatever one you like, some pneumatic collective mode, some magnon collective mode, whatever you like, which is made out of the electrons, and ask, can the electronic degrees of freedom lose energy to this collective mode? Hayu and Debanjan have a very interesting paper where they, inspired by this data, they introduce a collective mode, and the electrons can lose energy to the phonons, or the electrons can lose energy to the collective mode, which then loses energy to the phonons.
The electrons and the collective modes,
they're the same. Yeah, I should say that there's. Yeah. So, and that changes the power laws. And so, whether that is something consistent with our data or not, I don't know, but I think we need higher quality data. Yeah.
You assume you're sitting at the.
He had a poster, but you guys were in the elevator. Yeah. Yeah. I'm sorry, what? Say again? Oh, no. Yeah.
How low is the temperature to which the energy relaxation rate goes? What's more than a momentum one? Sorry, maybe I guess you could.
Our lowest measured temperature. So things start to look very different once you go into the superconducting state, which is also interesting. It's just not something we've talked about and thought about much about. But down to TC, you saw the data, right? It's well below.
You've also done this on protein glutamate, like a Fermi liquid. Could you just qualitatively say what looks different? Like, is it also a factor of 15?
It's similar looking, yeah. Yeah, you wouldn't know from the data that you were looking at strontium ruthenate versus the cuprates.
And there, do you see a dip that eventually at high temperatures starts to lose energy?
No, so one of the problems, at least this set of data, is that a parabolic metal with only elastic scattering has no nonlinearities, right? So there's no nonlinear response. We don't really care about why we have a nonlinear response. It could come from non-parabolicity. It could come from strong energy scattering. But we kind of need that as a tool to see this thing. And we start to lose the nonlinearities above, they start to get very weak above 150 Kelvin. I don't know what's the highest temperature, Will, you've measured anything at, but it's about 150 Kelvin, right? Yeah, something. Yeah. Sorry, yeah, go ahead. Yeah, that's what I said, I thought, yeah. Yeah, I don't remember exactly what I said. What I meant to say was, yeah, energy independent scattering, yeah.
Is there any difference? Didn't tell us how would we be able to tell? Showed us.
It's roughly the same, but I'm not making a big deal about what we need to do is to go in and look at power laws and do a kind of more, I think that's where the things that need to be done are. Yeah. Okay, good. So yeah, I'm going to be completely out of time. I have 10 minutes left. Yeah, that's fine. I had a part 3, but we're not really. Maybe I'll just say that. But I added one more slide just because this came up in. We talked. Dimitri talked a lot about ferromagnetic metals, and so this is. I didn't put the conductivity spectrum in here, but this is calcium ruthenate. So calcium ruthenate is often a material which has a crossover to a mod insulator, but if it's strained or pressurized, it becomes metallic and ferromagnetic. And so this is the resistivity as a function of temperature. Okay, this is here it is the optical conductivity. My apologies, it's right here as a function of frequency, and it actually has a kind of weird form, right? There's actually a little dip in here, and then those are the DC values, and they have to connect in some particular fashion. We measure DC and then we measure the terahertz. But there's clearly some kind of narrow low frequency feature. And if we characterize that as a function of temperature, that's here in purple. And in fact, it shows this peak and then comes down. That's actually very similar to the theory that Dimitri was talking about. And the thing that I would point out behind that theory was the notion that close to the ferromagnetic transition, you have scattering off of ferromagnetic collective modes, but there you have this critical slowing down. And so their energy scales are small, and so they can be taken as approximately elastic. And so we see that even though there's this very sharp feature through the ferromagnetic transition in calcium ruthenate, the energy relaxation rate just sails right through. You don't see that at all. So I think that's interesting. Yeah. Okay. Good. I have a few minutes left, and yeah, maybe I'll just give a recap and then I'm just going to tell you about something for the future. It's part 3 and we're going to have about 5 minutes for it. So I'll just tell you more or less in words what we're doing. But a recap on that, this 2D coherent terahertz spectroscopy, you're all experts now. We need theorists. There's a lot of theorists here. The spectrum, as I've made the point a number of times, the spectrum are complicated, right? It's nonlinear response is more complicated than linear response. We like linear response, and if we're going to go do things nonlinear, we're not just going to do them to, kind of show our experimental capacities. We want to do them for good reasons because we can get important information out. Sometimes the way we do that is by mapping, as we often do in physics, mapping them to systems we already understand. But those mappings can be interesting and they can be hidden. And so, I'd like to have more conversations with people about that. But I think that there's really a tremendous amount to do here and you can get unique information. I gave you a few different examples, spin systems with fractionalized spins, disordered systems, where we had evidence for, we called this marginal Fermi glass, nonlinearities in interacting metals, measure the energy relaxation rate in cuprates, non-Planckian, if you will. There was one other point about the cuprates here, and I mentioned the scale of the nonlinearities. Cuprate superconductors in their normal state is actually the most nonlinear metal that anybody has ever measured in the terahertz range. And that's presumably because the energy relaxation rates are very energy dependent. So, that's an interesting point people made now about 10 or 15 years ago in the terahertz community, a big deal about nonlinearities in graphene. And so cuprates in the normal state are 3 to 4 times bigger. So I'm not counting superconducting states. Superconductors are very nonlinear just in general. So I don't have a comparison to what bigger or smaller, but there are interesting dependencies.
But they're very nonlinear.
But all superconductors are very nonlinear. Yeah. You break, as you drive a superconductor at large currents, you start to break charge carriers, and that changes the conductivity at finite frequency. And so, whether they're more or less, we've done work on niobium nitride, a conventional superconductor. Cuprates are not any more nonlinear than niobium nitride, about the same, I would say.
So what if you go with the fluctuating?
Yeah, that's an interesting question. So we have an unpublished paper, not because anybody didn't like it, we just didn't get back to it. It's on the archive, on niobium nitride, very disordered films of niobium nitride. And so you work in a regime where KFL is, it's dirty limit, as we discussed today. It's 10 or something. So this is not a clean metal, but it's also not it's not something where KFL is close to 1. And the nonlinearities just die like an order parameter. You start in the superconducting state, warm up, the nonlinearities just die like an order parameter, and they're basically 0 in the normal state. As you disorder it, and we worked on a bunch of samples as we get close to the metal insulator transition, and you get down to KFL at about 2 or something thereabouts, the nonlinearities kick up, and by the time you get to KFL 1 and you get, or half, and you get the metal insulator around the range, you get the metal insulator transition, the nonlinearities in the normal state at niobium nitride, clean niobium nitride has a TC about 14 Kelvin, and these nonlinearities persist all the way up to like 30 Kelvin. I don't know what to make of that. Yeah. So we speculate about all kinds of things that you can imagine in our paper. Yeah. Okay. Good. So I have indeed 5 minutes left. So let me just put up the final thing, and it's really just kind of this was the title I gave to Leo, Quantum Optics for Quantum Materials. And so maybe we'll just skip ahead to this business here. Good. I've talked about response functions, right? All classical response functions, classical complex response functions, can be emulated by a superposition of potentially many classical oscillators, right? So it doesn't matter how complex a spectrum I have. You know this now, right? So if I can imagine I have some response function, it has some dissipative response, as we've discussed. I can always emulate that spectrum by some number of classical oscillators, right? It may be that that's not Occam's razor would tell me that there's other explanations for it, but nevertheless, I can emulate it. And then by Kramers-Kronig, if I've done a good emulation, I've also emulated the imaginary part, right? Because the Kramers-Kronig relations are linear, right? So I may need quantum mechanics to tell me why a coefficient has a particular value, a width, or a frequency, or something like that. But to emulate the spectrum itself, it's a classical response function, and I can emulate it with classical oscillators. So the question is, can we do spectroscopy where we can use some aspects of the quantum mechanical natures of light to find things which are intrinsically quantum mechanical correlations? And so my most honest answer